So let's tie a few things together, pun intended. The idea that, just to review, the idea that the shear walls tie to the foundation to prevent their overturning, their connections to the floor assemblies. So our shear wall, our foundation, our floor assemblies, the idea that our beams and column systems can be tied to our shear wall in order to create a more integral system. Many times in wood framing are involving clips, in concrete construction, rebar, in steel, weldments, and other kinds of fixtures going on to tie all of these elements together, but not just to bear gravity load now, but to these twisting and turning forces that our buildings are exposed to. And in the simplest way in wood framing, we have, once again, and I presented this before, but now to talk about it in kind of a review context, we have up here at the top here, we have a wood framed wall on a foundation system. Obviously nothing to support it from any kind of movement. So we put in our bolts to hold our sill in place. I talked about these being 6 foot on center, but I think the code now has moved to 3 foot on center for these. So we're not just holding, so when you see these, we're not just holding the building to the foundation, but we're also trying to create this building from sliding on the foundation in a reaction force to what is created by the shear wall, that stiff shear wall that shouldn't be doing any overturning because it's tied to the floor above it or tied to the floor deck below it. So a movement prevented by bolts, movement prevented by plywood shear panels. So in this case, we now have, you can see the assembly here where we have a wall framed once again with a floor deck this time on top of it. A load, could be a seismic load, could be a wind load, but we're all looking for those loads to be resisted by the shear wall. And without the plywood diaphragm, the shear wall is not a shear wall. No bracing in it. The plywood provides that kind of bracing or diaphragm activity. And notice once again, we have this idea of the nailing scheme, something that you would pay attention to if you were on site. Typically, we're talking about 4 and 6 inch spacings on the edges of the panels and on the seams. And then in the field, which typically the center of the panel, that could be 6 or 12 inches, depending on what the specifications are for that. So we have this idea of the foundation, the connection of the wall to the foundation, the shear wall then to become a performative shear wall. And then what happens with that, not only now we're not just concerned with how it's connected at the bottom, but how it's connected at the top. So we have another floor deck, and we're trying to prevent that kind of movement again. And I'll move my head so you can see these kind of Simpson strong ties. That's typically the brand manufacturer of these clips that allow multiple nails to go in to establish a really strong connection between that shear wall and the floor deck to transfer that shear wall activity. Many ways to make shear walls, a few ways here not to make shear walls. So 1 and 2 are just the wood frame and metal frame walls with plywood diaphragm on it in order to create a shear wall. We have a concrete masonry wall with reinforcement in it. And we have CMU units with rebar reinforcing placed through it both horizontally and vertically, and then the cavities filled with concrete. 5 would be a way you wouldn't make a seismic wall on reinforced brick masonry, but a way to reinforce that or make it perform as a shear wall would be to have a width of space between them, 2 widths of brick, and then fill that with rebar and concrete to create a shear wall type performing assembly. And then I probably should have put this right after we talked about the wood frame bracing. I just want to touch on this again. The idea we can make shaft walls out of something that isn't concrete. Why this comes up is if we're looking for reducing the carbon footprint, removing concrete from the building, we're going to need other solutions for that fire break or that fire stop between spaces, especially on egress and elevator cavities, shaft walls. And so there are manufacturers like USG that make these specific types of shaft wall material. Typically, I think it's 1 inch thick by panels that are 2 foot by 8 foot. They're just monstrous panels, very heavy to move. But they come with a metal clip system that allows you to put those slide one panel into the next, fasten it up, and keep the fire rating for that whole assembly. And these have been extensively tested to make sure that they perform as needed. And then, so this is many times an elevator shaft kind of application, but we can also do that stair shaft wall construction. So here we have rated assemblies constructed out of gypsum wallboard to a UL standard, based on just the use of drywall and many times steel framing systems. And then a few more graphics. Heavy timber bracing. This is just a graphic of a real in-the-field heavy timber bracing system. This is a company I put in. I actually worked for them for about 10 months or so as a sales engineer. They make buffers, hydraulic fluid dampers that absorb energy from motion. So these are used in buildings to, as I described in the first lead-in slide of this section, to absorb the energy of the motion. And so these are used extensively in retrofits and new constructions throughout California and, in fact, the world. A concept that's becoming popularized now with the idea of just building resilience in general, resilience we're classically understand building resilience is to climate change and the environmental effects, but to make a building seismically resilient. In California, buildings, if you think about it, if all buildings are exposed to an earthquake, if they're all damaged and need to be rebuilt, it's a colossal failure. Even though the building doesn't fall down, many times there are internal structural damage to the building. And classically, our design for seismic retrofit in the building is to keep the building from falling over during an earthquake and killing its occupants. It isn't really to make sure that the building continues on in its normal life. So this is an emerging kind of science and discussion, this idea of seismic resilience. And a lot of times this, and I think this will go to the hyperlink of it, wood timber comes into the discussion because of its elasticity, as opposed to concrete and reinforcing rebar, where you could have cracks and damage to the masonry that could be actually undetectable and very difficult to correct. So just something to keep in mind, this idea of seismic resilience has probably become an increasingly large part of the dialogue of earthquake design, especially in Southern California. So a couple of other links to obviously there's just tons of links to the idea of buildings and seismic resistance. And then I just wanted to touch on this idea of the moment frame. Obviously another way, I think we've learned this and discussed this in class, the idea of you can have a steel braced frame to create shear wall performance. This could be a structural retrofit or for a seismic issue. But we may need openings. So the idea that the moment frame is available to us to create a strong shear wall type assembly. Notice how they're bolted to the floors, strongly bolted to the floors. These have typically, they're not as stiff as a brace system, but in many cases that can be advantageous in order to create flexibility that's needed in the building at the same time, that sense of resilience. That idea of design options. And this is just a reminder that a lot of what we'll see in these seismic retrofits become design aesthetics for the building. And so it's an opportunity for us to create, really better visual solutions while still maintaining the requirements of the engineering requirements of creating a high-performing earthquake-resistant building. Just a couple of parting graphics here. This is a metal frame building, probably with I didn't talk on the idea of soft stories. I would like to include that probably in another presentation. I'll try to remember that. But here we have a metal frame building, and something that you can start to recognize now when you see something like this on a site, this idea of this X-bracing here. So these are laid over the steel studs in order to create that shear wall kind of stiffness. probably importantly done on this building because it'll probably not be clad in a plywood, but it'll probably be clad in a gypsum fiber reinforced gypsum wallboard material. And then that idea of the challenge, this is the last vision. I was thinking about where is the shear wall performance in this roof plane here, and what's happening in order to keep this whole assembly upright like this. And I don't have all the answers for it, I think, but this would be this would be something really to bear a lot of consideration when you're designing this now. I think without thinking about shear wall performance, without thinking about earthquakes, we would probably gloss over the fact that there doesn't appear to be hardly any kind of shear wall resistance at all within this assembly. The only places I can see maybe an indication of that is this tie off of the floor deck here to this. Maybe this is a floor diaphragm that's connecting at enough points along here that this floor deck is creating, and this has enough shear wall performance in it to cut down on, to create enough shear wall to keep this supported during wind loads. It almost looks like this elevator shaft or something isn't even connected to the top floor deck. So maybe these reach outs are actually times to tie up these columns in order to create shear wall performance. So the last key word is and sugar.